And when you do all of this algebra over here, what you're going to end up getting is 11 over 25, or in decimals, 0.44. Right, so let's write that result up here. So we got R5 is 11 over 25, or 0.44. Right, so that represents the sum of the areas of all of these rectangles here. Right, so notice that because we're dealing with the right endpoints, the area under the actual curve is going to be less than this area, right? As we showed with R4, but notice that R5, it's smaller than R4. 0.44 is smaller than 0.46875. So here we knew the area under the curve has to be less than this, but now we know the area under the curve has to be less than that. So notice we're tightening up that interval, and it's because we're using more rectangles. So we have an expression for R5. Let's do L5. Right, so let's redraw this again. So we got the parabola. I'm going to make it kind of wide. So we got an x value of 1. Then let's split it up into 5 intervals again. So we would have, let's do 1 over 5, 2 over 5, 3 over 5, and then we got 4 over 5. And what I'm going to do is for these x values, I'm going to put points. But now, these points are going to be the left upper corners of the rectangles, right? We're finding an expression for L5 in this case. So this point here is going to be the corner for this rectangle. And then we're going to have a rectangle here, right? The left corner of that rectangle is this point. And then we're going to have a rectangle here. Like that. 1, 2, 3, 4, 5 rectangles, right? This one's not really a rectangle because that width is 0, but let's include it anyway. So now this L5 is going to be the sum of the areas of these rectangles here. So let's get that expression. Notice the length of all of them is still going to be 1 over 5. So this is going to be 1 over 5. But we're going to be multiplying it by 0 squared. And then this rectangle, the length is going to be 1 over 5. The height of it is 1 over 5 squared plus 1 over 5. The height of it is 2 over 5 plus 1 over 5. Three over 5 squared plus 1 over 5, and then we'd have 4 over 5 squared, like that. Right, so that's going to be the expression here for the area of these 5 rectangles. And when you end up doing all of that in your calculator, you would end up getting 6 over 25 or 0.24. Right, so that is the sum of these areas here, of these rectangles. So that's going to be L5. Let me write it up here. L5 is 6 over 25, which is 0.24, like that. So notice that notice the area of these rectangles here, right? It's smaller than the area under the curve. We've mentioned that before. When you're using the left corners of the rectangles, that area of those rectangles, the sum of the areas, is going to be the less than the actual area under the curve. So notice that with this, we know the area, the actual area under the curve, it's going to be greater than 0.24 and it's going to be less than 0.44. And notice how this interval compares to this interval. It's a tighter interval, right? Between 0.24 and 0.44, that 0.44 is less than this number, 0.24 is greater than that number. So because we use more rectangles, we're getting a better approximation. We're getting a tighter interval. And that's the pattern that I wanted to show you, that the more rectangles we're using, the better the approximation is going to be. So if we split this interval up into 100 rectangles, right, this interval is going to get a lot tighter. We're going to get a better approximation. The problem is if you think about it, if we follow the exact same process that we just did, it's going to be really tough, or it's going to be very time consuming to draw out the 100 rectangles and then sum up all of those areas. So is there a better way to do this? And there actually is. And so what we're going to do is now we're going to come up with a general expression if we're using n rectangles, right? Where this n here can basically be any integer, right? So not 4 rectangles, not 5 rectangles. We're going to come up with a general expression when we're dealing with n rectangles.